In this video, we're going to be reviewing function vocabulary, domain of functions, and transformations of functions. We're starting here with function vocabulary, question number 26. We have a group of graphs here, and it says, which of the graphs represents an even function? Now remember, even function means that the graph has y-axis symmetry. And so looking at the graphs, A has no symmetry at all. B does have y-axis symmetry. If I folded that graph on the y-axis, it would match up. So B, actually I guess I'll write the answers out over here. C does not have y-axis symmetry. D does have y-axis symmetry. Not E. F is an even function, y-axis symmetry. G doesn't have any symmetry at all. H does have y-axis symmetry. I does not. All right, let's go to the next question. In this one, which of the graphs represents an odd function? Odd functions are graphs that have origin symmetry. They're symmetrical through the origin. I like to think about that as diagonal symmetry, that whatever's going on in quadrant 1, the same thing is happening in quadrant 3. And whatever's happening in quadrant 2, the same thing's happening in quadrant 4. So again, looking at our graphs, A has no symmetry, B was an even function. C, we do have that origin symmetry. What's happening here in quadrant 1 is the same thing that's happening in quadrant 3. And what's happening in quadrant 2 is also happening in quadrant 4. So C is an odd function. D was even. E is an odd function. F, we figured out, was even. G has no symmetry. H was even. I, that's another odd function. What's happening here in quadrant 1, same thing is happening in quadrant 3. Next question, which of the graphs is always decreasing and concave down? Well, graph A, that graph is always decreasing. And notice that the curve is opening down. That is an example of concave down. So A would be an answer for that. Graph B, the first part of this graph is decreasing and concave down, but the second part of the graph after we cross the y-axis, this part of the graph is increasing, and so that doesn't fit our description. Graph C starts out decreasing, but right here it's increasing. Also, it starts out concave up, so that's a no. Graph D is always concave up. Graph E is changing concavity. We're concave up and then concave down. F, same thing. G, always concave down, but it is increasing, so it also doesn't fit the criteria. Graph H has no concavity. Remember, whenever we have straight lines, if there's no curves, then you can't be concave up or down. Graph I, this graph is always decreasing. We're decreasing here, but it's not always concave down. This second piece right here is concave up. So the only answer for 28 is answer A. Number 29, which of the graphs has a relative minimum that is also an absolute minimum? Graph A has no relative minimum at all. B, we've got a relative minimum here, and that is in fact the lowest point on the graph, the absolute minimum. So B is an answer. On C, we have a relative minimum here, but it is not the lowest point on the graph because the graph keeps going. D, we've got a relative minimum, and that is the lowest point, the absolute minimum. On graph E, this graph is a little tricky. Probably should have made the graph itself bigger. It's supposed to be a graph of the sine function, y equals sine x. And if we look at it as sine x, then this is a relative minimum, and it's also going to be the absolute minimum. It's just going to occur infinitely many times as the periodic function repeats itself. So E is an answer, but if you didn't have that one, it's really not the best cropping of that graph. F has two relative minimums, and they're at the same y value, same function value there. It is an absolute minimum. G doesn't have any relative mins or maxes. H only has a relative maximum, and I, no minimums or maximums. So there's your answers, B, D, E, and F. Next question, which of the graphs has an inflection point at 0? Remember, an inflection point is the point on the graph where concavity changes. Graph A doesn't change concavity, it's always concave down. Graph B is also always concave down. Graph C, it is concave up and then concave down. And so this would be the inflection point right here, and that is at x equals 0. So that is one of our answers. D, always concave up. E, we are concave up and then concave down. So inflection point there at x equals 0. On question F, graph F, concave up here and here, concave down right here. So we do have inflection points here and here, but neither one of those are at x equals 0. So F, while it does have inflection points, they're not in the right place. So we're not going to include that one. G does not change concavity. H has no concavity. And I, it does change concavity. We're concave down, and then we're concave up, but we don't have an inflection point. The concavity changes because of this vertical asymptote here. So while we do have concavity change, there's no inflection point. So our only answers are C and E. And next question, which of the graphs changes concavity but does not have an inflection point? Well, we just looked at that, and that is graph I. All right, this next section, we're looking at domains of functions. If you remember when we talked about all of your parent functions and their domains, there's only 3 types of functions that have a limited domain. The rational function, the square root function, and the natural log function. And so we have one example of each of those here in this section. On part A, we have a rational function, and with a rational function, the denominator cannot be equal to 0 because you cannot divide by 0. So I'm going to say x squared minus 4 cannot be equal to 0. And then we need to determine what x values would make that equation 0. So I'm going to factor. Anytime you have a quadratic or an exponent, you need to factor to be able to solve. X squared minus 4 factors to x plus 2, x minus 2, and that cannot equal 0. So that means that x cannot be equal to negative 2 or positive 2. And so my domain here is going to be all real numbers, x not equal to negative 2 and positive 2. All right, next up, part B is a square root function. And for square roots, remember that whatever is under the square root, it must be positive, which means this expression 2x minus 5 must be greater than 0. It could also be equal to 0. So I said positive. I should have said it must be positive or equal to 0 because we can square root 0. Square root of 0 is 0. So we're going to include 0 here, and we're going to solve for x. 2x is greater than or equal to 5. X greater than or equal to 5 halves. And so that's going to be your domain, x greater than or equal to 5 halves. Or it could be written in interval notation as 5 halves. Notice I'm using a bracket to include 5 halves to infinity. And infinity always gets a parentheses. Lastly, we have the natural log. And remember that the domain of the natural log function is greater than 0. We can't natural log negative numbers, and also you cannot natural log 0. And so in this case, 4x plus 7 should be greater than 0. Not equal to, only greater than. And then we'll solve for x. 4x greater than negative 7, x greater than negative 7 divided by 4. So we could express our domain that way, or if we want to use interval notation, negative 7 over 4 with the parentheses because it's not included, to infinity. Either one of those would be correct answers. All right, in this next piece, we're looking at transformations of functions. And on these, for these graphs, we're shown a parent function and then a transformation of that parent function, and we're asked to write the equation of the transformed graph. So in this first one, question number 33, we have the absolute value function. That's our parent function. And it has been reflected over the x-axis. And so that means that we're going to make the absolute value negative. There's also been a horizontal shift here to the right of 3 units. And so y equals negative, that's for the reflection over the x-axis, absolute value of x minus 3. And notice I'm putting that minus 3, grouping it with the x because it is a horizontal shift. All right, number 34, looks like our parent function here is the square root function. And this time it's been reflected over the y-axis. If I reflect over the y-axis, that transformation is going to be a negative x. We're going to have that negative sign, but it's going to be on the x. And I've got a vertical translation of 2. So y equals the square root of negative x. That's to get the reflection over the y-axis. And then plus 2 for that vertical translation. All right, next up, looks like we have an x squared graph here. It has been, actually we've got 3 transformations that have happened here. It has been reflected over the x-axis, and so we know we're going to make our function negative. We've got a vertical shift of 1, but notice my new function is a vertical stretch of the original function. It's a little skinnier than the original function because it's been stretched out. And if I mark this point right here on the graph, normally with the parent function parabola, we go over 1, up 1, and that gives us a point on the graph. But with this transformed graph, we're going over 1 and down 2, and so that tells me that we've been stretched out by a factor of 2. And then I have x squared because that's our function, but we have this vertical translation of 1. So I have negative 2x squared plus 1. Finally, our last graph here is the parent graph is the natural log function, and we've got a horizontal translation of 1 unit. And notice that the transformed graph, that no part of that graph is negative anymore. We've got this sharp turn right here. And whenever we see a sharp turn on a graph like this, often that can indicate that we've used the absolute value as a transformation. And that's what's happened here. The negative piece of the graph has been flipped up and made positive. So y is equal to absolute value of the natural log of x, and then I've got this horizontal translation. Oh no, I'm writing over the watermark. Let me write this. I'll write it here above the graph. Y is equal to absolute value of the natural log of x minus 1. That's that horizontal translation but the whole natural log function is being absolute valued. All right, last question for this video, 37. We've got a graph shown below, tangent to the x-axis at x equals -3. That means it just touches the x-axis right there at -3. It doesn't cross it. We have a 0 at x equals 0, and a relative minimum that has the coordinates -1, -4. And the question here says, which of the transformations, those 8 transformations that we've been studying in class, which of them would result in a graph with a relative maximum at x equals -1? And there's several, we got a few possibilities here. At x equals -1, right now I have a minimum. And so if I want to turn that into a maximum, one way that I could do that is by reflecting the graph over the x-axis. And that transformation would be -f of x. So that would be one correct answer to this question. Another way that I could do it, because this piece of the graph is negative, I could make all of the negative values positive by absolute valuing the function. And that would also turn that minimum into a maximum. And another possibility would be, notice we've got a maximum point here at -3, and we could just shift the graph right 2 units, so that maximum point would be at -1. And so that would be f of x minus 2. So all 3 of those are possible transformations that would result in a new graph with a relative maximum at -1. This next one, which of the transformations would result in a relative minimum at x equals +1? So this time, we want our minimum to be at x equals +1. Right now I have a minimum at x equals -1, and I want to move that over here to +1. One way that I can do that is by reflecting the graph over the y-axis. That transformation is y equals -x. If I put negative on the x, then all my x's change signs, and so that -1 would become a +1, and I would have a minimum there. The other thing I could do is just shift the graph right 2 units, f of x minus 2. And finally, which of the transformations would result in an absolute minimum at x equals -3? All right, so if I have an absolute minimum, that means that it's going to be the lowest point on the graph. Nothing else is going to be lower. Now notice with this graph, it's going to go all the way to positive infinity and all the way down to negative infinity. And so if I just do a reflection, I'm still going to have a piece of the graph that's going all the way to infinity. This is going to involve, if I'm going to have an absolute minimum, then I need to take all of this negative part of the graph and make it positive. And I can do that with the absolute value. If I absolute value the whole function, then the positive part of the graph stays, but the negative part, let's try that again, becomes positive. I'm really not drawing a very good graph here. There we go, that's a little bit better. And then here at -3, I would have a absolute minimum. And that's really the only way to cause an absolute minimum to happen at x equals -3.